Welcome back. Unit 1, Domain and Range, Day 2. Again, your corresponding textbook pages. Yesterday it was a little long-winded. I'll try to shorten that down a little bit. I apologize for that. I like to keep my videos under 20 minutes, so I will work on that more. Okay, so what we're going to do now is we're going to look at these in terms of real-life scenarios. We're going to try to interpret domain and range in them. So in this case, I'm looking for the domain and range in set notation for this particular scenario. We've got speeding in a school zone and a fine. The speeding will determine the amount of the fine, therefore my speeding will be my x and my fine will be my y. Therefore I write it in an ordered pair format. Our speed determines the amount of the ticket. Now if we take a look at some of this situation here, we'll go ahead and just set up some ordered pairs to help us get started. So if I'm traveling at a speed of 20 miles per hour, I will receive no ticket, therefore the fine will be 0. If I go ahead and ramp that up to 25 miles an hour, let's take a look at it. It says the fine in a school zone is $200 plus $50 every 10 miles per hour. Okay, so I haven't gone 10 miles an hour over the speed limit yet, so that means my fine will still only be $200. Okay, so the additional fine begins when a car is clocked at 30. So let's go ahead and clock that one and see what happens. So at 30 miles an hour, I go up $50 in fines, so that's $250. So on and so forth until I get to the value of 40, because it says every 10 miles per hour over, so that means it's now at 300. So I think you can see the pattern occurring here, and let's go ahead and set that up. Well, now we're going to do it in set notation, so remember we have to define our domain as x. And we have to start at a value. Well, the value that we start at has to be 20. Now, even though on a radar gun it will only show it in terms of whole numbers, we could write it as an inequality if we wanted to. All right, but to show how we can write this as a set of value of numbers, we'll just go ahead and do like the radar gun has. Okay, so we go 20, then 21, then 22, then 23. Now we have a good understanding of about how fast or by the interval we're counting up by, we can go ahead and dot, dot, dot this thing on it all the way up. Now, it doesn't say how fast the car is going to be going, but we can reasonably assume that a vehicle is not going to travel until infinity as far as its speed is concerned. All right, so we would put a reasonable rate of speed here at the top end of most cars. So let's go ahead and just make an arbitrary number of 100. Now we're going to go ahead and define our range as y. Now, when we're not speeding, we're not going to get a fine. So we're going to start with 0. Between 20 and 30, we'll receive a ticket, and it'll be $200, not $250. Got ahead of myself there. Between 30 and 40, $250, so on and so forth. And then it goes up to 300. Now you have a reasonable understanding that they were counting by 50s every time, so I'm going to go ahead and put that continuation, dot, dot, dot. And now this is a very important part of our range. Can't go any more than $500, no matter how fast we're going. And there's your domain and range. Number 2. Along those same lines, a typical cashier at a grocery store checks out customers at $10 per hour. All right? Well, let's go ahead and think about it in terms of ordered pairs. All right? So the number of grocery store clerks will determine the amount of customers that can be checked out. Okay? So that means we're going to have grocery store clerks and customers. So if I don't have any grocery store clerks, I can't check out any customers. If I have 1, that's 10, 2, that's 20. I think you get the picture about what my domain and range is going to look like. Again, what is the reasonable range for this situation in roster notation? Okay, well the range is the y values. We're going to start at 0. I can get 10, 20, 30. You can see I'm skip counting by those 10s now, so I'm going to go ahead and use that continuation symbol there. And then what's the maximum amount that I can check out? Well, let's think for a second. If I have 20 checkout stations, That means I have to start at 200 customers. All right, moving on. Questions number 3 and 4. Question number 3 through 14, it says state the domain in interval notation. Interval notation is where I'm going to be headed here. All right, so let's think for a second. Y equals 2x minus 10. So that's y equals mx plus b. What is that? Oh, that's linear. All right, linear functions have no restriction on their domain, and that's the word we're going to really start to explore today is restrictions. Therefore, the interval notation for that is negative infinity to infinity. All right, y equals 3x squared. Ooh, that would be a parabola. That's a quadratic. All right, a quadratic function has no restriction on its domain. Therefore, it will go from negative infinity to infinity. All right, in questions number 5 through 7, we're going to explore one of our 2 domain restrictions for today. This is known as a rational function, otherwise known as a reciprocal function. Reciprocal functions go everywhere. That means that their domain is negative infinity to positive infinity, except where the denominator is 0. Very important. This is our restriction for these 3 problems. All right, so let's take a look at it. First thing we're going to do is we're going to identify when the denominator equals 0. So I'm going to say, okay, the denominator, and I'll abbreviate it here for time's sake, the denominator equals x. And we know the denominator cannot equal 0, so I'm going to do a little substitution here. X cannot equal 0. Now in most of these cases, you guys are going to be able to see this right away, and you're not going to have to deal with this. But I'm going to continue to do it this way so that you can really pick up on what I'm doing here and how to get this restriction down every single time. All right, let's go back up to what I stated earlier. Reciprocal functions go everywhere except when the denominator is 0. Well, in interval notation, that looks like this. Negative infinity to 0. And remember, we have to pick up that union symbol because we have another interval, and 0 to infinity. Looks like that. All right, next, we're going to go ahead and take a look at this one, a little bit more complicated. Again, the denominator equals x plus 2. I know the denominator cannot equal 0, so simple substitution. X plus 2 cannot equal 0. Subtract 2 to both sides. X cannot equal negative 2. All right, again, negative infinity to negative 2. Ooh, caught myself there. All right, union, negative 2 to infinity. All right, go ahead and take a look at that one. Solve it on your own. Pause the video. All right, hopefully you guys are doing that part because it's really important that you're getting a little bit of this understanding on your own before you just barrel through it with me. All right, the denominator equals 2x minus 1. The denominator cannot equal 0. Simple substitution. 2x minus 1 cannot equal 0. Adding 1 to both sides. 2x cannot equal 1. And dividing 2 to both sides gives me x cannot equal 1/2. Therefore, my domain, negative infinity to 1/2. Pick up again on the other side, 1/2 to infinity. All right, question number 8. Now we're getting into the second domain restriction that you're going to learn about today. Domain restriction number 2. When you have a radical, that's these symbols right here, and the index of that radical is even. Remember, a square root is 2. So that's 2, 4, 6, 8, so on and so forth. You cannot have a negative radicand. Oh, the radicand. That's the number inside the radical. I know I'm throwing all these terms about. Okay, so notice what I wrote here. A root with an even number index with a negative radicand gives you an imaginary solution. We'll study more about imaginary solutions later. All right, so again, the radicand, and I'll go ahead and abbreviate that for you, equals x. I know the radicand cannot be negative. How do I write that? Oh yeah, greater than or equal to 0. All right? So that means simple substitution, x greater than or equal to 0. And now I'm set and ready to go. Again, it said interval notation, so I'm going to start there, bracketing 0, continuing on to infinity. All right, radicand equals x plus 4. Radicand has to be positive. How do I write that? The radicand must be greater than or equal to 0. All right, so that means that I get x plus 4 greater than or equal to 0. Subtract 4 to both sides, and I get x greater than or equal to negative 4. How do I write that? Negative 4 to infinity, bracket, parentheses. All right, again, pause the video, go with number 10, see if you can get it. A little bit complicated, not too bad though. All right, hopefully you're ready to go on this one. The radicand equals 3/4 x plus 1. So radicand must be greater than or equal to 0. So 3/4 x plus 1 greater than or equal to 0. Subtract 1 to both sides, and I get 3/4 x greater than or equal to negative 1. Now, remember, we don't divide fractions, we multiply by their reciprocals. So remember that, multiply by their reciprocals. So x must be greater than or equal to negative 4/3. How do we write that? Negative 4/3 to infinity, bracket, parentheses. All right, moving on. Question number 11, question number 12, question number 13, and question number 14 give you some practice in looking at the different types of parent functions you're going to encounter over the next semester or so, and which ones have restrictions and which ones don't. Remember, we've only studied 2 restrictions so far. Therefore, any other function that doesn't follow the restriction has no restriction. Okay? So number 11, that's a 3. That's an odd numbered index. Because we didn't say anything about odd ones, only even ones, there is no restriction. Since there is no restriction, that's negative infinity to positive infinity. All right, on this one, oh, there's that even numbered index. That means we've got that restriction. So the radicand is 7x minus 1. And remember, the radicand must be greater than or equal to 0. 7x minus 1 greater than or equal to 0. Add 1 to both sides. 7x greater than or equal to 1. Divide by 7. Greater than or equal to 1/7. Remember interval notation. 1/7 to infinity, bracket, parentheses. Well, these symbols are funny, but they're not a denominator, nor are they a radical, so there must be something else. These are absolute value symbols. We're going to study about that coming up very shortly, but it's important for you to understand that it's not one of the 2 functions that we talked about having a restriction, therefore it does not have one. We didn't say anything about these. We only said indexes, not exponents. Therefore, there again is no restriction. All right, remember there's only 2 restrictions that we've studied so far. All right, number 15. This one throws a new wrench into it. I've got a radical and I've got a denominator. So let's address both of them separately, okay? Let's first start with the denominator, okay? I'm going to leave the radical off for just a second. The denominator equals x plus 7. The denominator, what was that one again? Oh yeah, x cannot equal 0. So it's x plus 7 cannot equal 0. So subtract 7 to both sides, and I get x cannot equal negative 7. All right, now let's deal with it as a radicand for a second. So the radicand is x plus 7. What do we say about the radicand? Oh yeah, it has to be greater than or equal to 0. So x plus 7 greater than or equal to 0, subtract 7 to both sides. X must be greater than or equal to negative 7. Okay, let's think about how these 2 can be used together in the same domain. So if it can't be equal to -7, it can be greater than. So that means the only thing we're going to change about our restriction is that it's not going to be a bracket, it's going to be a parentheses. Okay? All right, moving on down to the last three here. Now, if you have any questions about how I got that one, please ask, because I know that one's a little bit confusing. We just look at both of them together. All right, in this one, we're going to write a possible function that will have each of the following domains. Okay, so remember, we're looking for the one that goes everywhere except for the value around the union symbol. All right, so that's got to be the denominator one. Okay, so what value makes that not possible? So let's think backwards for a second here. Okay, so the only value that x cannot equal is 3. All right, so I'm going to solve this backwards. In order to move this over to the other side, I got to subtract it. So I'm going to subtract -3 to both sides, and I get x minus 3 cannot equal 0. Now it looks a lot like what we talked about before. Now we're going to go ahead and say, okay, the denominator was equal to x minus 3 because that's how we substituted it in the first place. So x minus 3, and I can throw any number up here I want, so I'll go ahead and put 4. All right. All right, something that doesn't have a restriction. Let's think of all the parent functions that don't. All right, so linear, so y equals x. That's a good one. Absolute value, y equals those vertical lines. That's right. What about cubic? Cubic's a good one. That's y equals x to the third. So on and so forth. I'm sure you could come up with some other ones on your own. And now we have this one. All right, so that symbol right there looks an awful lot like it's a radical symbol, so let's go ahead and do that. X greater than or equal to -5/3. All right, -5/3. Now, the first thing I would think to do is just add 5/3 to the other side, but I don't want to do that. What I want to do is I want to move the 3 and the 5 as two separate numbers. So let's go ahead and start by multiplying both sides by 3. That gives me 3x greater than or equal to -5. Next thing I'm going to do is I'm going to add that 5 to the other side. +5, +5. And this just gives us a cleaner, more proper algebra problem. Okay? That's why I did that in 2 steps instead of just adding 5/3 to the other side. This looks a lot cleaner than just having that fraction sitting over there by itself. Okay? So that's why I solved it in 2 different steps. Okay, so now this is the radicand. Remember, we're doing that substitution. We're solving backwards. 3x plus 5. So I'll just go ahead and write that in a square root symbol to keep it simple. 3x plus 5. Looks like that. Please make sure that if you have any questions, you ask them for me at the beginning of class tomorrow. I know some of this stuff can be a little bit confusing, and we'll go over it a little bit more if you have any questions at the beginning of class.